Hey guys, in this video, we're going to talk about how to find the equation of the tangent plane of a surface defined by an equation at a given point. Right now, what we have is a surface defined by z equal to 2x squared plus y squared, and then the given point is 1, 1, 3. Before we solve this question, let's take a look at a theorem. The theorem says that the gradient of f at a given point x0, y0, z0 is going to be a normal vector of the tangent plane of this surface defined by this fx, yz, the exact same function equal to 0 at the exact same point x0, y0, z0. In order for us to use this theorem, we will need to have a function, right? And also we will need to have this function equal to 0 representing the exact same surface defined by this equation. And we know that this equation is not given in that way. So we need to construct a function fx, yz in order for us to use this, okay? Because we have this equal to 0, so it's natural for us to think of moving everything to one side. So we're going to move z to the right side, which is going to give us 2x squared plus y squared minus z equal to 0, okay? And then we're going to define fx, yz by this, okay? Define fx, yz equal to 2x squared plus y squared minus z. So right now we can make use of this theorem, right? We just calculate the gradient of f. That's going to give us the normal vector of the tangent plane. After we have the normal vector, we can use the, what is that called? The point normal form of the plane that is from 1300 to figure out what the equation is. Okay, so let's find the gradient of f. Gradient of f is going to be partial x, and then partial y, partial z. Okay, going to be looking at this function here. Partial x gives us 4x, and then partial y, that's 2y. Partial z, -1. Notice that this is just a general gradient expression. We need to find that specific gradient for this given point, that specific normal vector. So we need to substitute x, y, z with 1, 1, 3 to find that specific gradient. So this gradient 1, 1, 3 is going to be, right, 4x is going to be 4, and then y equal to 1, that gives us 2, and then z is constantly -1, so it doesn't matter what the z value is. So now we have our gradient here, okay? So that is going to be the normal vector of the tangent plane. In the pictures, it looks like that. Let's say this is our surface, okay. And then this is the point that we are working on. So a tangent plane, tangent to this surface at this point is going to look like this. Okay. You're going to have a normal vector pointing in this way. That's going to be our gradient f. Also, that can be denoted by the normal vector n. Okay, normal vector n. Okay. And then we recall the equation of a plane from 1300. That is a times x minus x0 plus b times y minus y0 plus c z minus z0 equal to 0, right? So that's the equation of a plane with normal vector ABC, right? Normal vector ABC, which is this one, A and B and C, right? Representing the normal vector. And then x0, y0, z0 is any random point that is on the plane. In this picture, we can see that because this plane is tangent to the surface at this point. So this point is on the plane. That being said, we can just use this point as our x0, y0, z0. So we have x0, y0, z0 being 1, 1, 3. And our ABC being the normal vector 4, 2, -1. Okay, so we just need to fill out all this with the information that we know. So we have this being 4 times x minus 1 plus 2 times y minus 1, and then plus c, which is the -1, times z minus 3, okay, equal to 0, which is going to be the equation of the tangent plane of the surface at this point.